Well, good afternoon, everybody. It's nice to see that we have a very good audience today, and it's very appropriate for two reasons. One is the speaker, I'll tell you about him in a minute, but the other one is that this is the last colloquium of the season, and so nice to have people here celebrate. We don't know yet what's going to happen next year because I'm told that this building is going to be razed to the ground in September, which is not very helpful for us. So we're trying to find out whether we can find another place. We may, but it's not sure. So enjoy today. And also, you know, there won't be any food here at 3:45 next week. Anyway. So today our speaker is Tim Tait. Tim is an associate professor of theoretical physics at UC Irvine, and he received his PhD in physics at Michigan State in 1999. Then for 2.5 years, he was a research associate as a theoretical physicist at Argonne. Then he went to Fermi Lab for 2 years, then he went back to Argonne as an assistant physicist for 5 years, and during that time he also became an assistant professor of physics at Northwestern University. But since 2009, he's been at UC Irvine. He's authored a lot of papers, over 60 journal publications, and he's received several prestigious grants, the latest one being one from NSF to study the nature of dark matter and electroweak symmetry breaking at colliders. So it's no coincidence that Tim is here today to explain to us why we're looking for the Higgs. Tim, thank you.
Okay, thank you very much for that very kind introduction. It's always a pleasure to visit SLAC. As you just heard, I'm going to talk about why it is we're looking for the Higgs. Particle physicists tend to use the word Higgs without adding boson to the end. I mean, sometimes they do, sometimes they don't. Hopefully I'll explain sort of how to precisely distinguish the Higgs field from the Higgs boson. I'm going to apologize to the particle physicists that this talk was not really aimed at you, but I hope that it's enjoyable anyway. And just to cover the question that I most often get, this animal is an anteater. It keeps in a glorious tradition of nice UC mascots. All right, so an outline of what I'll talk about today is we'll start off talking about what the Higgs boson is. I think that's sort of the most important thing that frames the discussion, because when we see what it is, we understand what its value is, and therefore why it is we should look for it. But then hopefully at the end, I'll explain how it is that we're looking for it, or at least the main way that we're looking for it. And this, I think, is also important because, as we'll see, we're sort of at a crossroads where we're likely to actually find it sometime in the very near future. And so it's fun to see sort of the language we use to talk about how we look for it, because then when we do find it, you'll understand what it is that people are saying in a more technical way. And then finally, I don't really have a whole lot of, I didn't think I had a lot of time left, so I didn't put a lot of material here, but I'll say a little bit about what finding it actually tells us. And one other thing, the lecturer in me really likes it when people ask questions in the middle of the talk rather than saving them for the end, so please feel free to do that. I never have yet. Okay, so the first big section is to talk about what the Higgs boson is. And you see here I did put the word boson because that is really what we're looking for at the Large Hadron Collider. So first we have to talk about the Higgs boson in popular culture. If you look online, you'll find that you can actually buy a Higgs boson. It only costs about $10.50 plus shipping. I think that's where they get you. Unfortunately, this advertisement on the web, while very attractive, I have to say I want one, didn't tell me how much it weighs, and so we still have to measure it at the LHC. Also, you'll notice that there's actually some inflation going on here. The image says $9.75, but you can actually buy it as part of the entire Boson Pack, which is only $52. I think my niece, who's now 5 weeks old, is probably going to get one of these for Christmas. All right, but kidding aside, or actually I think it's really fun to see how science inspires popular culture. And my attitude is always that we have to keep doing science because I'm sure that as we get better scientific results, we're going to get even better responses from the public. So that's my sort of taking inspiration from their taking inspiration from me. But to begin with, let's start off with a definition. And this is not supposed to make sense written this way, but the idea is that then we can fill in all these pieces and we'll understand actually what we mean. So the Higgs boson is the particle corresponding to the quantum fluctuations of the Higgs field. And the Higgs field is the thing that gives masses to the fundamental particles of the standard model of particle physics. I will very often just say standard model because in my line of work, this is assumed. And I'll sometimes abbreviate it on slides as just SM. So please keep that in mind. So the first thing we have to understand in our definition is what a quantum field is. So first of all, what's an ordinary field? An ordinary field, absolutely everyone in this room understands. It's just something that takes a different value at every point in space and maybe time. So for example, if you measured the temperature in this room at every point, you all took a little thermometer and wrote it down, you could make a map of the temperature, and maybe it's hotter on one side and colder on the other, but you would have at least a snapshot of what the temperature map or the temperature field looked like at that moment in time. So the fields that we're going to talk about are more abstract. They still are physical things. They have physical consequences. Like, for example, we could do the same trick where we measure the electric field in the room. And there aren't big electric fields over most of the room, but we could still measure the small ones that are there. And so that's a field. The fields we're interested in are relativistic. They're functions of space and time. And none of that is really all that important for what I'm going to say. But what is important is that they're quantum fields. Now, there's actually a textbook written by a SLAC professor, Michael Peskin, on quantum field theory. So if you have any questions at the end of that, you can go find him. Or you can ask me. But the important thing for the quantum field, the important concept we need from quantum field theory here is that in a quantum field, it's not just some quantity that takes a value at every point in space and time, but there are little ripples that move around in it. So these little ripples are quantum. Quantum just means discrete. They come in little discrete packets of energy. So this is sort of supposed to cartoon that. Now we have a particular little ripple of the field, maybe here or here, and it moves around. And the point is that because they're discrete, we can actually count how many of these there are. So we can describe actually the state of what's going on inside this box by specifying how many of these little packets of energy we have in it. And this is really how particles emerge from quantum field theory. When we say particles, we just mean these ripples in the quantum field. And so every particle that we know, like the electron, for example, is actually a wave, that is a quantum ripple in a quantum field. So part of the reason to belabor this point is that there's a distinction between the Higgs boson and the Higgs field. But this distinction sounds more mysterious than it really is, because really everything that we know at the fundamental level is a quantum field. So the fact that we would talk about the Higgs field is not at all surprising. And when you get down to it, I have to say that talking at least as a theoretical physicist, what I really care about are the underlying objects in the theory, and that would be the quantum fields themselves. But the reason why we end up talking about particles is that there's a correspondence between the particle, which is just a ripple in the field, and the rules that govern the behavior of the fields. So by studying the particles, we get to learn about the field. So, and we're going to go through this in more detail. But what makes the Higgs boson different is that it's actually a field that seems to be turned on throughout space, meaning that if I were to measure the amount of Higgs in empty space, and so that's cartooned here by these two panels. In the top panel, we've got the Higgs field. It's turned on, meaning that there's some amount of Higgs everywhere in space. And then there are also maybe Higgs bosons. Those would be the ripples that are moving around in the field. And those are the particles on top of it. So hopefully now the distinction, at least, between the Higgs field and the Higgs boson is becoming clear. The Higgs field is really sort of, if you want, the fundamental object. And the bosons are the ripples in it. And those are the things that we're looking for because they're easier for us to manipulate. And this is different than the electron. The electron is also a particle that is a ripple in a quantum field. But the electron field is mostly zero. So it's not very interesting in empty space. And therefore, we focus just on the little packets or the electrons themselves. So a lot of it, the rest of this, at least the rest of this section of the talk, is going to be actually discussing why it is we want to have this Higgs field that's turned on throughout space, and what that means. All right, so the moral of this part of the story is that the Higgs, and you see there again, I left off boson or field, like every fundamental building block is proposed to be, because we haven't discovered it yet, a quantum field. And so that's not really surprising, but what is unusual is that the field seems not to be zero in otherwise empty space. So when we look for the Higgs boson, what we're really doing is just looking for some particle that is the tangible sign that that Higgs field actually exists. Okay, but of course, this raises a new and more interesting question. Why is it that we want the Higgs field to be there and to be turned on in empty space? And to talk about that, we have to talk a little bit about the standard model of particle physics. It's the theory of everything that we know how to describe so far. So it contains all of the matter particles that we've discovered. And so this is kind of like a periodic table. These are the matter particles. They're arranged into quarks. These ones in pink. The leptons are the green ones. And force carriers in blue. And the Higgs actually really is part of the standard model. It's a necessary part of it. So it really belongs on this table, but we don't usually put it because we haven't discovered it yet. So it's down here with a question mark. I should also mention, even though I'm not going to say anything about any of these very exciting topics, but the standard model is still missing a complete description of gravity at all energies. It's missing dark matter. It's missing dark energy. So there are actually a lot of things we do need to add to it. But I think the most pressing one, as we'll see, is the Higgs itself. So in the quantum field theory picture, the particles exert forces on each other by exchanging other particles. So if you use electromagnetism as an example, here are two electrons coming in, and they interact with each other. That is, they know that they're both negatively charged, that they're supposed to repel each other. So this one will deflect this way, that one will deflect that way. Because there's a cloud of photons flitting between them that tells them basically that each other are there. So the electron field interacts with the photon field, and that's how the force is transmitted. The weak nuclear and strong nuclear forces are very similar. They have a little bit more complicated mathematics that we don't really need to get into. And so if we go through the force carriers, and you'll see why this sort of elementary stuff is important in a second. We just saw the photon. The photon is what mediates the electromagnetic interaction. So any electrically charged particles feel forces on each other. They exert forces on each other because of the existence of the electromagnetic field or the photon field. I won't say very much about the strong nuclear force. It's what holds the proton together through gluons. And I should have actually pointed out, I put little check marks here so you can see who interacts with who. So the gluons interact with the quarks, and they hold them together. For example, two up quarks and a down quark are the proton. And the weak nuclear force, the W and the Z, interact with essentially all of the matter fields. And they're responsible for things like neutron decay and neutrino interactions. So here's a cartoon of neutron decay. We start off with a neutron. That's one up quark and two down quarks. One of the down quarks actually is transformed into an up quark. So this neutron becomes a proton. And it does that by interacting with a W boson, which itself actually is a virtual particle that produces, at the end of the day, an electron and a neutrino. And hopefully this is important sort of to explain why it is we really do need the Higgs when we get to that point. Because it turns out that these particles, the W and the Z, have very high masses. So the Higgs is really responsible for generating mass, and we'll see how that works with them. Yes?
On your periodic table, the charge force carriers are arranged in a certain order.
Yeah, I have to say I would not probably have chosen that order if it were up to me. Yeah. Now, roughly speaking, we have the photon and the gluon that are both massless, and then the W and Z that are more massive, but I don't necessarily think that that's the right way to organize them. And actually, for the quarks, they've done the opposite. Well, for the quarks and leptons, they've done the opposite. So, yeah.
That picture, I think we might explain why, in certain cases, that W comes up. I mean, this doesn't happen all the time. So.
No, that's right. You know what? I actually have something about that later on, so I will get to that. And this is good. Yeah, please, more questions.
Yeah. Was the Higgs there at the inception of the Standard Model?
That's sort of a tricky question because the Standard Model historically grew, things are never clear at the beginning. So, in its cloudy origin, but yes, it was basically there from the very beginning. And that's because we knew from the very beginning that these force carriers were very heavy.
Would you please repeat the questions when they're asked, because we can't hear the questions?
Sure, I'll do that. Okay. The question was the Higgs there from the inception of the Standard Model? And the answer was yes. Usually I get my grad students to ask questions by staring at them, but there's too many of you to make that efficient. Okay, so now we're going to go a little bit more into the mathematics of how these force carriers work. We're going to use electromagnetism to illustrate the physics. I have to apologize, there's a very small amount of calculus in the next two slides. It's not actually important for the discussion, but it's neat, and if you, do understand it, it makes things very clear, so that's why I included it. So we're going to use electromagnetism to illustrate the physics, but we have to keep in mind that the photon is actually part of the Standard Model that does not get a mass and therefore does not feel the effects of the Higgs. So this is really an analogy where I talk about sort of the mathematics of how I describe electromagnetism, but what I really have in mind are the force carriers that are the W and the Z bosons. And if it's not clear, you've proven that you will ask questions, and so I will rely on you to do it. Okay, so to begin with, when we learned in freshman physics, the EM field can be described by a scalar potential and a vector potential. We call the scalar potential phi and the vector potential A. And given these two potentials, they tell us what the electric and magnetic fields are. Remember, the electric field is E and the magnetic field is B. Okay. And of course, these symbols just tell me to take derivatives of these functions to tell me what these fields should be. And relativistically, actually, we would say that both the phi and the A vector field form a single four-dimensional vector potential, and that's because everything is relativistic in the sense of Einstein. This is a personal note. When I was an undergraduate, I took great delight in deciding that since the physical things, the things that make charges move, are E and B, these potentials, A and phi, were not worth my trouble. As you're going to see in the next few slides, I'm not going to talk about E and B at all, but instead I'm going to talk about the potentials, so the joke was on me. Okay, so there's something else that we learn when we study electromagnetism, and that's that these choices of the potentials A and phi are not actually unique. And what I mean by that is that given a physical system, a given electric and magnetic field, the choices of the functions A and phi that describe that system have a certain, I'll use the word symmetry. What I mean by that is that there is more than one choice that leads to the same electric and magnetic field. So there's different ways of describing the same physics with different choices of phi and A. And in particular, the way that works is if I take any function of space and time, so that function here has been written as lambda, and so lambda is just anything that depends on space and time, and I shift these two potentials by the same way, E and B don't change. And again, if you understand the calculus, you'll be able to see that this shift in these equations actually leads these guys to stay unchanged. It's very neat. So the point, though, is that, and this is actually why when I was undergrad I didn't like A and phi. It's because you couldn't tell me really what they were. You could just tell me a set of them that would all lead to the same physical result. So we call this in physics, this choice of this function lambda that lets me shift or redefine my potentials, the choice of gauge. And so we call the symmetry, right, symmetry because nothing physical, meaning E and B, nothing physical changes if I change the potentials. That's a symmetry. It means something's not changing. And since all the physical quantities are independent of the choice of the function, I can really choose it any way I like. And of course, the way you learn this when you first encounter it is that some problems, sometimes when you want to solve for what the electric and magnetic field should turn out to be, the solution's much easier to get if you make a good choice of lambda. And it seems just like a curiosity. When you first meet it, you think, OK, that's weird. I have to choose a gauge. But actually, it has really deep and important implications. And I would say that this symmetry, this fact that I can redefine the potentials in this way, is actually the most significant thing about electromagnetism. It's the thing that tells me the most about it, actually. And so the first consequence it has is that because the system has a symmetry, then there's a theorem that was proved by M.E. Noether that because of this symmetry, there's a quantity that's conserved. That means something doesn't change with time. And the thing that doesn't change with time is the electric charge. So it's sort of cartooned here, where if I keep track of the amount of electric charge in a little volume, it's related to the amount of current that carries the charge out or flows in. And this is, I have to say, as a theoretical physicist, I find this really deep and beautiful. There's a connection between the presence of symmetry and something being conserved by the dynamics of, in this case, the quantum fields. It's also very practical. As an engineer of theories of nature, this is telling me something important, because since I know that electric charge is conserved as far as I can measure, I now know how to engineer that fact into a theory. If I build in this gauge invariance, then the theory will automatically conserve the electric charge. It also tells me a lot more than that. It actually tells me something about the structure of how particles, really fields, are interacting with each other. So it turns out that just building this symmetry into the theory restricts the way particles are allowed to talk to each other. And that's because if I write down interactions between the fields at random, in general, the things I write down are going to break the symmetry. So I have to make sure I only write down things that actually preserve this symmetry. And again, it's obvious that all things have to conserve electric charge, since that's what the symmetry tells me. But it tells me a lot more, too. So here are sort of a cartoon of some examples. For one thing, it tells me that actually the electron has to interact with the electromagnetic field. Once I know the symmetry is there, there is no way around that. It tells me how it interacts and how strongly it interacts. And I think that's where I got hooked on particle physics, when someone told me that, hey, there's a symmetry that tells you not only that charge is conserved, but also that the electron has to talk to electric and magnetic fields. It also tells me that other interactions are not allowed. So for example, the muon, which is just a heavy sort of copy of the electron in some sense, it's a particle whose mass is bigger than the electron, but its other properties are the same, is not actually allowed to interact with the electron and the EM field. Or at least it's not allowed to interact naively. And we can get into the non-naive stuff later if we want. So the point is that if I want to write down this theory, knowing the symmetries there is really powerful, because it tells me I can only write down a few kinds of things. And so if I were to try to write down a general theory of all those force carriers with all those matter fields, I would write down hundreds of terms. And the symmetries actually reduce this number to a very small handful of terms. Yeah?
In quantum mechanics, wouldn't the gauge be changed from a function lambda to the unitary group of one complex variable?
All right, the question was, in quantum mechanics, wouldn't the gauge transformation change to a complex number, which is a unitary group of one variable? Did I repeat that more or less right? OK. And the answer is that yes, that is actually the sophisticated mathematical description of the symmetry. So in fact, if you were talking to someone who's sophisticated in mathematics, as you clearly are, I would just tell you that the group is U1. OK. So, and to illustrate that point, what I've done here is taken two different images. The first one I found by Googling it on the web. This is all of those, and don't try to read them. I can't even read them from this close or even on my screen. The point is that this is the entire set of interactions of the standard model of particle physics expanded out without knowing about the symmetry. And so you can see that it's got a lot of different items contained in it. The top one is the one that I typed in myself. And this is actually sort of the minimum description I need, knowing that the symmetries are operating. And it just reinforces the fact that there are literally hundreds of things to worry about if you don't know about the symmetry, but only a very small number to worry about if you do. So the symmetry is, I said the symmetry is really powerful. If I tell you what the symmetry is, and in this case, since it's the whole standard model, I have to talk about more than electromagnetism, but I can specify the entire symmetries. And then, knowing a little bit more than that, I can actually write down the standard model very easily. And so this is what 't Hooft called being under the spell of the gauge principle. Really, as far as we can tell, these gauge symmetries are specifying how nature works. So they seem to be very fundamental. And whether that turns out to be true or not may even be a philosophical question. But in the very least, it's clear that they are very good ways or very efficient ways for us to understand the structure of the theory that we're dealing with. It's actually a bit more than a recipe. The symmetry does more things for you than that. If you've studied electromagnetic radiation, then you know that electromagnetic radiation comes in two different polarizations. So if the wave is traveling along this black arrow, it's sort of pointing upwards this way, then there are two different polarizations corresponding to whether the electric field is oscillating along this axis. So you see as I go back sort of along the wave, the electric field gets bigger, smaller, goes the other way, keeps going back and forth like that. The magnetic field is always at right angles to it. So I can either have the electric field along this axis and the magnetic field along the one that comes out of the board, or I can have the opposite. The opposite polarization is where the electric field is coming out of the board and the magnetic field is in the plane. And we know that there are only two ways they can be polarized, but we're describing our theory in terms of four potentials, and that would really mean there should be four independent kinds of electromagnetic waves. So another thing that the gauge symmetry is really reflecting is the fact that not all the components of those potentials are physical. And so in particular, two of the components actually just correspond to stuff that doesn't actually describe electric or magnetic fields. It actually just tells me which gauge I'm choosing to work in. So the message here is really that the gauge symmetry is also important because it actually takes sort of the general four potentials of the electromagnetic field and maps it or tells us that some parts of it are redundant, and therefore it cuts out the parts we don't need to describe these things. So that's great. I hope I've convinced you that the gauge symmetry really is an important and essential sort of part of the description of nature. Now, it's a challenge, though, when we want to describe massive particles. So we have to understand why the gauge symmetry is actually in conflict with the idea that the particles have masses. And then once we've done that, we can understand how it is that the Higgs boson will come to, the Higgs field really, will come to the rescue and allow us to have both massive particles and the gauge symmetry. So we have to talk about massive particles. And in quantum field theory, or relativistically even, the mass of the particle is the minimum energy, the energy it has when it's not moving. For a quantum field, the mass looks like a contribution to the energy density, right? And since the field is actually something that fills all of space, I don't talk about its energy. You know, I could tell you how much energy is in the box, but then you'd say, well, what about the energy outside of it? But instead, we just talk about how much energy there is per unit volume. So the energy density is proportional to the field. In this case, we have our potential squared, and then times some parameter, which is the mass of the particle squared. So this is the energy cost for the field to exist. It tells me that if I want to turn on the field, it costs energy, and the amount it costs is described by this parameter m that is the mass of the particle. So in my cartoon, as we go to larger values, we can start off with, say, no energy, turn the field on, get to some energy, and then there's lots of energy up there. Now, I should also mention, even though I'm not going to do anything with it, that there are these ellipses. They describe the fact that, or they remind me of the fact that it costs energy for the field to change value, or in other words, for it to go from nothing to something, and that corresponds to kinetic energy. So there is also some energy every time this field changes value. But the important thing for our purposes is this energy that corresponds to the mass. Okay, so the gauge symmetry tells us that the physics is unchanged if we shift the potentials, but then we saw that the energy actually, at least the mass part of the energy, contains the potential itself. So if I do one of these shifts I'm talking about, the potential shifts, and so does the energy. And if the energy is changing, that means that the physics is not staying the same. So what that tells me is the only way that this formula for the energy can be right, together with the gauge symmetry, is if the particle has zero mass, because then the thing I multiply this by is zero, and so when I do a shift, it's multiplied by zero, and it doesn't actually change the energy at all. And for the electromagnetic field, the photon and the gluon, this is no problem. But the W and Z's are observed to have big masses. So we know that actually we have to have massive force carriers here. That's just measuring their masses. But we see a problem because we also want gauge symmetries to describe their interactions. And so hopefully this will get back to sort of Greg's question. The mass is very important. And this is, again, our cartoon of the neutron decaying. The fact that the W boson has a big mass has really dramatic practical consequences. So in fact, the W boson in this image, so the W boson is about 80 times more heavy than the neutron itself. So there's actually no way that I can conserve energy if the neutron decays into a W boson and a proton. The W is just it takes way more energy to create a W boson than I even started with in the neutron. But that's all right. It still appears as a virtual particle. So virtual particles just means that we don't really have enough energy to produce it. It's sort of only here as a mediator. It mediates between this change of the down quark to the up quark, and then turns into much lighter neutrinos and electrons, and I do have enough energy to produce those. So the fact that the W is much more heavy than the neutron makes the probability for this happening much less. In other words, if I want to borrow energy temporarily, the amount that I can get typically, the probability of me being able to get that much energy goes down as I ask for more and more. And so what this means is that the likelihood for a neutron to decay into a proton in this way is much less likely than it would be if the W boson had been massless, the way the gauge symmetry said it should be. If the W boson had been massless, then neutrons would decay like crazy. They would just disappear. That would be really bad for the universe that we see, because if neutrons decay quickly, they would disappear from the universe. We wouldn't have time to put them together into heavy atoms, and I think it's fair to say that we probably wouldn't at least be here in the form that we are talking about it. So it's actually a really important thing that the neutron has a long lifetime. Long lifetime in this case means something like 10 or 15 minutes. All right, so now we have a problem. I spent some time motivating the need for the gauge symmetry, but found that it requires 0 masses for the force mediators. The W and Z bosons are measured to be some of the heaviest particles in the standard model, and we just saw we need them because we want our neutrons. The way that we get around the impasse is by introducing the Higgs field, and sort of when you first see it, the Higgs is really just another quantum field. It carries electroweak charge. As a result, it has to interact with the W and Z bosons, so there are interactions dictated by the symmetry. So we preserve gauge invariance. And from this point of view, there's really no difference between the Higgs field and any other of the matter fields, like the electron. It's just one more field that we included. But now the trick is that unlike the electron, the Higgs field is turned on in empty space. So what that does is it effectively generates a mass for the particles. And the way that works is, so imagine we have some empty space. So empty space means still filled with the Higgs field, and that's why it's shaded in this. I really couldn't tell you what color that is, actually. Now, if we have a particle like the W that interacts with the Higgs, and as it moves through this box, it keeps bumping into the background of field that it sees here. So it goes a little way, and then it interacts with the field. It gets knocked around, eventually sort of makes its way across. But it goes slowly because it has to keep fighting against this field that it keeps hitting. And it's just like when you are walking through a pool of water, there's a lot more resistance from the water than there is, say, from air. A photon, on the other hand, doesn't interact with the Higgs field. The Higgs has been engineered that way. And as a result, the photon just zips through. It never interacts with the background, and therefore it moves at the speed of light. And so this is not really an obvious definition of mass, but it does actually make a certain sense. So the mass represents the inertia of the particle, or how fast it goes when you give it a push. And I think we all saw F equals ma, the most important of Newton's laws, maybe. So what this tells me is that if I apply a force, the amount that I accelerate depends on the property of what I'm putting the force on, or the mass. So you could imagine measuring the mass by just letting particles go on this end of the box, and then say, OK, I gave them a little push. I know how much push I gave them, so therefore I know F. And if I want to know how much they accelerated, then, if I measure their speed that they end up with, then I know how much they accelerated, and therefore what the mass is. And from this notion of mass, I see that everything works just fine. I give the particle a little push. The photon will zip right through, and I'll say, OK, great. That guy didn't have any mass. The W boson meanders its way through. All right, that had a big mass. The electron is actually something in between. The electron does have a mass. It does interact with the Higgs field. I didn't really tell you very much about that, but It's similar. The difference is that the amount that the electron interacts with the Higgs field is not actually dictated by the symmetry. So I can make that whatever I want. And in particular, to describe the real electron, I make it something pretty small. So the electron tends to go pretty far before it bounces, and therefore it goes through much faster than the W boson. It has a smaller mass. Any questions about that? Yes.
The wandering W boson, it's interacting with the Higgs field. What is the nature of that interaction again?
Well, so the question was, so the W boson as it wanders through is interacting with the Higgs field, and the question is, what's the nature of the interaction? I think the right way to think about it is sort of more along the lines of it's just sort of bouncing off the field in the sense that, you know, it goes through a small, in this sort of, it's a cartoon somewhat of the description, but it goes through a small change in direction.
We were taught the idea that interaction takes place via exchange particles.
That's right. So think about it more along the lines of, what if there was an electric field turned on in space, right? Then I know that if I had an electric field, let's say it's all pointing up towards the ceiling. If I take a test charge and I let it go, it'll just drift up. So think about it along that lines. It's really no different because what we call the exchange of the particle is just a ripple of the field. So therefore, it's really no different than the fields interacting themselves directly. And that's sort of why I spent some time on that at the beginning, because I think that's a really good concept. Yeah.
If people want to be disturbed about this, it would be even more disturbed if they took into account the fact that you said that these particles are virtual. So what does it mean that a virtual particle is interacting with this field?
All right, so Greg's question is, what does it mean that a virtual particle is interacting with this field? That's a good question. It means that you couldn't actually do my sort of Gedanken experiment where you let the W boson go and let it drift because it's virtual, at least in the process like neutron decay. I think what you always want to do is remember that what we call the particle, so I mean it's really tempting to think of particles as little billiard balls and see them sort of pinging around. But the reason why I started off talking about the fields, which we don't even usually, we usually don't even bother talking about the fields, even if they're the way we do calculations. I think the reason the concept of the field is important is that all I mean by virtual particle is a certain ripple of that field that wasn't quite right. If I get it right, then the ripple will travel a long distance. If I don't get the ripple quite right, if I don't make it the right way, maybe it bends too much over here or it extends too far out, then the ripple doesn't last very long. So a virtual particle is really just the field put into a configuration that isn't, it doesn't ring at that frequency, if you like. And so from that point of view, there's no difference between talking about the particle bouncing around and talking about the field. So in this case, what does it mean? There's sort of a configuration of field. It feels drag because it keeps, the fields are colliding with each other in some way. By the way, these are great questions. Any more? OK. So we still have one important detail left to discuss. We saw how particles swimming in a quantum sea of Higgs, I couldn't resist writing that, behave as if they were more massive because they're constantly bumping into it. But we would like to still engineer into the theory the fact that the Higgs should be turned on in the first place. And the way we can do that is by modifying the expression for the energy of the Higgs field. So this is, again, the energy density of the Higgs field. And instead of just making it the field h squared times some mass parameter, I've actually given it a slightly different form in terms of two constants. I called one of them lambda and one of them v. And this is not the lambda that we had before. So if I plot what this function looks like, it's a double well potential. It's got two sort of low points and a high point in the middle. The parameters, lambda and v, just control sort of, so v actually tells me how far from 0 of the field the minimum occurs. And lambda actually just tells me sort of how it behaves as it goes to very large values. Now, if I want to minimize the energy, I don't want to sit at 0 field, because 0 field has more energy than it does down here. Instead, I'd like actually the field to be turned on. And so we can just really engineer this expression for the energy into the theory. It turns out that it's gauge invariant, so there's no problem doing that. And the Higgs field, instead of sitting at 0, will actually sit at some non-zero value. And so it turns itself on. And that's how the standard model actually engineers a non-zero value for the Higgs field. So what this really means is that the energy of empty space is 0, or so you know that the absolute value of energy doesn't really mean anything except a gravity, but the energy of empty space is 0 instead of when the Higgs is 0, but when the Higgs lives out here. And so this is a trick we could use to turn on different fields if we wanted to. Yeah? So the question was, is there a difference between the two wells? And I have to say, that's also a really, really excellent question. It turns out that actually this cartoon is a little too schematic. If I include the gauge symmetry, then this thing becomes three-dimensional, and it sort of looks like a little hill sitting at the bottom of a valley, not even a valley, right, a hole. And the gauge symmetry actually moves me around the bottom of the valley. So since the gauge symmetry is just redundancy of how I describe things, it doesn't have any physical consequences. If it had literally been like this, then there could actually have been something.
Are there any other potentials of this shape?
So the question is, are there any other potentials of this shape? If you meant in physics taken as a whole, then of course there are a gazillion of them. But actually, yeah, this is the only particle in the standard model that has this kind of potential and therefore has a field that wants to be turned on. All the other, well, I should be very careful. The strong force is very complicated. There's some debate. It may actually also want to turn on some of its fields too. Stan Brodsky, who is looking at his computer right now and waving at me, is an expert on this. But so let's just say that the simplistic answer is no, no other field wants to be turned on this way, but with the asterisk that there is something to talk about for the strong force. Yeah?
If the E didn't go to 0 at the minimum, that violate gauge variance?
No, it doesn't. So actually, that's the reason this trick works, is that engineering this energy, and of course, there's a way, when I say engineer a theory, there's a way, right, of encoding the dynamics of the theory that I haven't said anything about at all. But this form of the energy is actually gauge invariant. So that means that E not being 0 at the minimum doesn't actually. Oh, you're asking about it if it's 0 out here? No, so actually, where this occurs, this minimum, is related to dark energy, to the cosmological constant. So in fact, if we take everything at face value, it may very well be that this potential is not quite hitting its minimum at 0, but at a very small value. And we really have no idea why that would be true, given that the amount of shift here would be really tiny compared to any of the other numbers that are in the theory. Yeah?
This sounds a little bit snarky, and I do not mean it to be so. But as an intelligent but naive person, it sounds like you're just using finagle factors to get from point A to point B. And it's okay to do one or two to kind of prove a point, but so far I think I've heard about 3 or 4 of them. And I'm going, when does this stop, and when do we start plugging in some real numbers?
OK, so the question is about finagle factors. And I have to ask you a question before I can answer it. So the question is, are the finagle factors in the way that I've described the theory? In other words, do you think that I'm the one doing the finagling? Or do you think that the theory is what's doing the finagling? Or are you worried about the distinction between the two, maybe?
Yeah, I will credit you with the fact that you are trying to describe the theory, but the theory gets done by somebody, and so maybe it's that person's finagle factor.
Right.
That way
Okay.
we should blame entirely into the theory.
All right, so to try to answer the question, I think I have finagled a lot of things in trying to sort of make this accessible, and that's because I didn't want to have to assume a lot of mathematics, because then you lose a certain segment of the audience, and I tried to get the ideas through. I actually tried to do them justice, but I think I did. I will admit, I did finagle a number of times, probably every single time I explained something. Now, maybe even more. Now, having said that, there is also a certain amount of finagling that you could look at just in this expression to say, well, why do I choose the parameters that I choose? Why does this sit right where it needs to? Those are good questions. I don't think we have good answers for them, honestly. I would say the reason we want to discover the Higgs is so that we can measure all of these things, and then we can have some idea as to whether or not it connects with something deeper.
Well, we are talking about the Higgs, and well, I'll
The audience might appreciate what the situation was before Higgs wrote his article, the problem with Goldstone theorem, and then we see that finagling was, there's some way we can finagle it and get mass.
I think that's right. Yeah, I'm obviously not going to go in that direction, but if you want, I mean, maybe it seems like it's a finagling. I like that word. It seems like you're finagling something precisely because you are looking at a contradiction. You have massive particles, but you have a symmetry that you really are very excited about, but that you can't reconcile. So if you want, this is actually a very slick trick for putting the two together. OK, so that used just about all my time. But hopefully it explains something about what the Higgs is. And so now we'll say a little bit about how we look for it. So what we saw is that the Higgs boson has to interact with particles to give them masses. So what's plotted here actually are all the fundamental particles that we know and what their masses are. And you can see actually this is a log plot. It's probably hard to read, but it goes from 10 to the 3 down to 10 to the minus 12. So we have a wide variety of particles. The neutrinos are very light. Even actually the lightest quarks and leptons are very light. And at the very top, the heaviest things should be the top quark, the W and Z, and the Higgs itself. So the real message to take away, though, is that the things the Higgs likes to talk to are the heavy guys. And we know that has to be true because it gave them mass proportionally to how much it interacted with them. So if we want to see the Higgs and therefore prove that the Higgs field is there and doing what we want it to, we have to look for processes that involve these heavy particles. So for example, if we look at Higgs production at the Large Hadron Collider, and I just wrote LHC without even writing it out, so I should apologize for that, all of the main processes. So what this plot tells you is how often you produce a Higgs boson as a function of its mass. So we don't know what the mass of the Higgs boson is until we discover it, and therefore we have to look at all masses. So this shows you the cross sections. The top one here is actually a process where two gluons come in, and they actually annihilate into virtual top quarks that then get together and produce a Higgs. So even if I don't have enough energy to actually produce real top quarks, I can still produce a Higgs boson. And you can see it's kind of neat. The virtual top quarks are acting like a bridge between the massless gluons and the Higgs, which doesn't like to talk to massless things. It has to go through a massive guy to get there. And so this rate is plotted here. And the significant thing to take away from it is that this is the dominant way that we make Higgs bosons, except for very, very, very high masses. You can see that this curve, and again, this is a log plot, is something like a factor of 10 bigger than the next rate. The next process, we have two quarks coming in. They each emit a W boson or a Z boson, and those two fuse together. Since they're massive, they like to talk to the Higgs, and we can produce a Higgs that way. That's the red curve. And then finally, the green curve is the process where we produce a virtual W or Z boson, and then it radiates off a Higgs and leaves behind a real W or Z boson.
What's the meaning of the line thickness?
Oh, that's good, yeah. The line thickness is actually representing how uncertain our knowledge is of that process. So we know how much the Higgs boson should couple to the top quark because we know what the mass of the top quark is, but we don't know it perfectly. We also know how likely it is to get a gluon of a certain energy out of a proton at the LHC, but there's some uncertainty in how often, on how likely that particular energy is. And so you put those factors together, and that tells you what the width of the curve is. So you can see that not only is this process the biggest, but it's also the most uncertain. And I forgot to repeat the question, sorry. The question was, what does the thickness of the lines mean? We also can talk about how the Higgs boson should decay. The Higgs is heavy enough that it'll decay very quickly, too quickly to be observed directly. So we can't actually just catch a Higgs boson and look at it. We have to look at its decay products. And again, it tends to decay most often into whatever the heaviest particles that are available. So this shows you as a function of the Higgs boson mass how likely it is to decay into a bunch of different channels. The width of the line still tells you the uncertainty. And you can see that for low masses, the Higgs boson likes to decay into bottom quarks, and that's because the W's and the Z's and the top quarks are too heavy. So the Higgs can't actually quite decay into them, and therefore that's the dominant mode. Once the Higgs gets heavy enough that it can decay into two W bosons, then that tends to dominate. Now, when we look for the Higgs, it's not enough to just look for the dominant way that it decays. We have to actually look for modes that we can pick out of the background of other things producing the same particles in the final state. And so it turns out that the mode that we use most, at least the mode we used for discovery, is actually often photon-photon. So at least for low masses, we use this very rare decay. It happens sort of a few times in 1,000, but it sticks out better, and so it's a better way to look for it. And the search is on. I'm sure you've heard this. In fact, there is a lot of participation here at SLAC in the ATLAS experiment. So what this graph shows is the number of events that are measured by this detector at the Large Hadron Collider. And they're plotted as a function of something called the invariant mass of the two photons. And all that means is just that if you imagine that these two photons did come from a single particle that was decaying, then given their energy, I can tell you what the mass would be. So the mass we would infer, if this is really what's happening, is m gamma gamma. And so you can see that there are predictions for what the standard model would like to produce even if there were no Higgs, and that's this red curve. And then on top of that, we have the actual data points. These are the black curves with the error bars. And you can see that, because we just count the events as they come in, sometimes you get a little bit more, sometimes you get a little bit less. It looks like that. And if we look at ATLAS's sister experiment, CMS, we see a sort of similar curve, again as a function of the invariant mass and data points. And you can also see that these points agree really, really well with this prediction. So actually, I think this is a big triumph of particle theory in itself, that we can really make predictions that work really well. And what we're looking for, of course, is a little bump that would correspond to a Higgs boson being produced on top. And so here CMS is actually giving you a cartoon of what it might look like. So you'd be looking for sort of a little upturn about that big on this big background. It's hard. All right, so this is the kind of plot that we see these days to talk about the Higgs. It's called the Brazilian flag plot because of the colors that they use. They're nice colors, I will agree with that. The plot is a little bit peculiar if you're looking for the Higgs boson, because it shows you as a function of the mass of the Higgs how many times bigger the Higgs signal would have to be than the standard model signal in order for them to see it. So in other words, if you had a Higgs that was being produced at the rate expected in the standard model, it would live wherever the mass is, and it would take a value of 1. It would be produced at 1 times the standard model rate. But since we haven't found the Higgs yet, what we do is we end up saying, well, let's say it was produced with some bigger rate. What can we exclude given the fact that we don't see any bumps in our data? So in this plane, the first thing we want to look at is this red line that's called the expected exclusion. And this just tells you, given the amount of data they collected, how well they would expect to do. And you can see from this plot that given this much data, ATLAS expects that in this channel for the Higgs decay, that they could probably exclude something like around twice a Higgs that is produced twice as often as it should be in the standard model. So they didn't actually expect to discover the Higgs in this data. They expected to come reasonably close. Then these colored bands, the green and the yellow colored bands, they tell you something about how often you'll get a different result than the one you expected. Because remember, some of those bins have a few extra events, some of them have too few. But you expect some fluctuations like that. So therefore, you wouldn't be too surprised if you ended up getting exclusions that were within the green or the yellow. And these are just the 1 and the 2 sigma variations around this expected exclusion. And then the most exciting thing is the actual data. So this is what they actually were able to exclude. And I'll actually compare that with the plot we saw before in just 1 second. But you can see that it also goes up and down, and it mostly stays inside the green area. So mostly you see the sort of fluctuations that are consistent with what you would have expected given how much data you took. All right, and I already pointed out, we didn't really quite expect to have sensitivity yet because this expected curve didn't actually cross 1 where the standard model lives. All right, so now let's compare some of the points. So remember, this is the invariant mass of the diphotons. So in particular, if I zoom in at these few points right where this arrow is pointing, you can see that they're all a little bit lower than the curve. That means that there was a deficit of events there. We didn't even get as much as we thought there would be if there were no Higgs. But that means it's not very likely the Higgs was actually living there, because it would have been adding something, and it would be less likely that we would fluctuate downward. And so in fact, if I look at that mass on this plot of the exclusion, I see that sure enough, I'm doing better than I expected. I can rule out, in fact, I can actually rule out a standard model Higgs even for a narrow range of masses there. And of course, if I look instead over at these points, I see that there's a few points clustered together that are all above the expected background. And so here, actually, I got a limit that was worse than the one I expected. I thought I could rule out something like 1.5 times the standard model production, but instead, I'm only ruling out something like 3.5 times. And it's a funny way to talk about discovering something. I'm actually telling you where it's not. That will hopefully change soon. Now, of course, when you see something like this, your temptation is not to say, oh, look, that's a really terrible exclusion at that mass. What you want to say is, well, if I get a terrible exclusion, it might be because I can't actually exclude it because it's really there. So that's sort of the peculiar psychology. When I see a bad limit, it's actually the first harbinger of a discovery. And in fact, because it goes outside of the yellow band, it tells us that this kind of deviation does happen, but it will only happen a few times out of 100 if I were to repeat this experiment over and over again. So it's not very likely, but it's not solid enough for me to say that I'm really making a discovery. So if you're thinking that maybe we're just barely starting to see a Higgs poking out of the background, the next thing you do is you check the other experiment. There are 2 experiments, so I could ask, hey, do you guys see an excess at the same mass? And the answer is that it looks like it's a little shifted, so slightly lower masses, but they do. So that means that gets you more excited. You say, hey, it might be that there's a Higgs living here. We're not sure yet, but if there is, at least it's consistent between the 2 experiments. And so this is an intriguing hint, but it's still only a hint. The LHC is running. It's collecting more data. It's at a slightly higher energy. If there really is a Higgs signal at 125 GeV, we should see it in the new data too. We can also look for some of the less sensitive channels, like a Higgs going to ZZ into charged leptons, like electrons. This is less promising as a discovery mode, but if you see a similar bump in the same mass, then it adds weight to your interpreting the signal as belonging to a Higgs. And actually, we expect that a big update was going to be announced at ICHEP, which starts on July 4th of this year in Melbourne, Australia. And I think a large number of physicists are going to Melbourne, Australia, because they're thinking that this may be where we see more hints that the Higgs is living at 125 GeV. Maybe I should be giving this talk in 2 weeks. All right, so yeah, I think I should leave some time for questions, but I want to say a little bit about what finding it tells us. So finding the Higgs boson, meaning waiting until we get enough data to say it really is there, it tells us something really important. It tells us that this whole theoretical framework of the standard model is correct at the level that there really is a Higgs there. There's still lots of room for additional surprises. What we want to do then is measure all of the different ways the Higgs can be produced in decay, because that tells us all its interactions with the fundamental particles. And that really tells us whether it is exactly the standard model prediction for the Higgs, or maybe it's something that's similar but not quite the same. So we want to measure, so we know how the Higgs is supposed to interact with all the standard model particles because we know all their masses. We want to see if there's anything unexpected. So this is actually a slide that was made by Michael Peskin, who's a professor here in the theory group. It shows you long-term how the LHC can measure couplings to different particles, including invisible particles. Those are not part of the standard model. And then also, for contrast, it shows you what you could do with a future facility. It's a high-energy E plus E minus linear collider. There are 2 different assumptions here for the blue and the red, to show you that actually, if we do confirm that the Higgs is there, this would be a very interesting machine because it would really let you pin down its properties much more precisely. You would go from uncertainties on these couplings that would be something like, maybe tens of % to something of a few %. And so it would really tell you with good precision what the Higgs is. So just to wrap up, and I have to say that what else you could find, how the Higgs could be non-standard, could easily be another 1 hour of discussion. But just to give you a few random thoughts, there may be particles that really don't like to couple to the rest of the standard model, so we can't produce them very easily at accelerators. But they do like to couple to the Higgs, so we can produce them that way. And there are some theories that have dark matter particles that fall in that category. So it could be that the Higgs decays into dark particles, and that's actually why Michael has an invisible decay mode here, is to anticipate that possibility. There could be more than one Higgs boson. Supersymmetric theories predict that there are multiple Higgses. It's going to take a lot of work, and it's going to be a lot of fun to figure out all these details so that we really can see if this is the standard model Higgs or something else. So hopefully what the message that it comes out is that the Higgs field is an important ingredient in our understanding of nature. It reconciles masses with the gauge symmetries that we needed to build the standard model and make a theory that's consistent with everything we see, both the masses and the symmetries. Seeing the Higgs boson is our way of verifying that the field is really there doing its job. We expect to have strong evidence about the existence of a Higgs if its mass is sort of around 125 GeV by the end of this year. So we should get a big update in a couple of weeks, and probably another big update at the end of the year. And I hear that Lance Dixon is taking bets about what the mass turns out to be and when it'll be discovered. So this is the beginning of what we need to do. Once we discover it, we need to measure its properties and make sure that it really is what we predict. And either way, I'm going to be really excited. So thanks for listening.